So, bonjour. You kept that rather short, I think, and of course I'm in awe of this incredible young scientist from Taormina, where I will be going to after this meeting. It's a real privilege to be here, and I will just take up a comment that Louisa made, that I returned from my postdoctoral period in Canada in late 1969, and I was relating and found out that Jean-Marie Lane here did not, of course, know of this detail, but I arrived in Southampton off the Bremen and drove up to Sheffield on my way to Edinburgh to join my family after, I think, more than a year. One couldn't flit back and forth across the Atlantic the way people do now. And the reason for stopping there was that this young Frenchman was on the speaker's agenda for the stereochemistry conference in Sheffield. And that, of course, was a must for me, because I had already got my eyes on the tetrahedron that was cited yesterday in 1968. And, you know, many of us are bio-inspired. I'm Lane-inspired. So, to that extent, I'm going to begin in the beginning with reference to a paper, in fact two that are back-to-back in biochemistry, published in 1989, entitled Interactions of Dimethyl Diazopyridinium Dication with Nucleic Acids. And the first one deals with, as you can see, the binding to nucleic acid components and to single-stranded polynucleotides and their photocleavage. The second one deals with the binding to double-stranded polynucleotides. Now, this beast has a rather long name, and for the rest of the lecture, I'm just going to call it DAPP. So my roadmap today, and I should say that the emphasis that I'm going to place, because I feel very strongly about this now, is how to take the science that we all enjoy as quickly and as simply as possible to commercial application. So I'm going to talk, to begin with, about the chameleonic character of DAPP, how we were able to use it to carry out exfoliation of graphene, and then from what we experienced in these two quarters, to go on to means of supramolecular encryption, and then finally to complete the loop, because Jean-Marie, with the late Claude Helene, had effectively started the activity of looking at the anti-cancer properties of DAPP. And then I'll make a kind of probably dramatic change and look at the supramolecular chemistry that turns to gold. And I think this is appropriate because, you know, we are celebrating out there in the auditorium here a 50th anniversary. And at least in the English-speaking world, I'm not quite sure about France and Germany and so forth, gold is associated with 50. So this is a golden jubilee effect. Yeah? All right. So back to the chemistry, very simple synthesis. Start with this dianhydride, aqueous methylamine, you get through to this thiamide, reduce it, and then oxidize. And in 3 steps, in reasonable yield, you have DAPP. It crystallizes. And what's interesting about the crystallization is that it stacks up in this repeating ABC column. And the reason for this is that its pi electron density is such that it's rich in the middle and deficient on the sides. And in looking at the crystal structure in more detail, these ABC repeats, which are in columns that the 3 of them, and the color picks this out, are differentiated, but they're related by a crystallographic inversion center, are repeated ad nauseum, so that you get a very long column in each case, and in between you have, for this unit cell, the 12 counter ions that you would expect. I think a very interesting way of looking at it is that the stacking is such that we get roughly a 60-degree torsion, if I might use that word, between the 3 DAPP groups, and this is, of course, repeated down through the structure. And this reflects itself at the level of the crystal. And so for a bundle of crystals here at larger concentrations, you can see that we get a bundle, and then if you carry out a crystallization on a silicon surface at a much lower concentration, you can actually get single crystals that grow to 10 micrometers in length. So this is happening because of something that's becoming very popular in the United States now. That is homophilic recognition. And, but of course, alongside that, we have the competing situation of heterophilic recognition. And we mustn't, of course, play down the heterophilic recognition. And so crown ethers, suitably endowed with pi electron-rich units here, will form a nice one-to-one complex with the DAPP. And here you can see the stability constant that is over 10,000 reciprocal molarity. In the case of bisparaffenylene 34 crown 10, there's room for 2 of these to come on. And I want to play up this whole business of 1 and 2 as we move around my quad chart, as it were, that is my roadmap. Somewhat weaker complexes, and of course it's a 2-stage binding, and you can see the 2-to-1 binding from the job plot over there in the right-hand corner. We, of course, looked at just capturing these units in terms of ritaxanes, and this could be done not in hugely efficient yields, but by using the very useful click chemistry. And we repeated it also with the bisparaffenylene 34 crown 10, and I'll come back to HP as we know him later in my talk. And then we asked ourselves, if we switched from crown ethers to using cucurbiturol, and this is the one with 8 glycol units that are being encircled, what would be the possibility that we could include 2 of these DAPP units in aqueous solution now, so we're working with the chloride. The quantum yield, because this compound really fluoresces quite remarkably when you shine UV light on it, is in fact increased quite considerably when you add the equivalence of CB8 to 0.5, which is indicative of a 2-to-1 complex. And again, the job plot bears this out. The fluorescence then plateaus once you have 2 of these DAPPs coming in from each side of this receptor. So again, you can get a snapshot of what's going on in the solid state from a 1-to-1 mixture. You see some free, of course, CB8, but what we also see are these DAPPs poking into the middle of the receptor here, such that you get a very nice molecular recognition match between the pi electron rich area here and the pi electron deficient area there, and vice versa. And here's another view looking down with a space filling representation of how these 2 are nestling inside the receptor. Then another interesting feature that I'm going to play to later is the fact that we get this overlap subsequently also of aromatic residues beyond the receptor unit. Right, so that's my first entry into DAPP. So we just summarize what we've seen, that we can complex it with these crown ethers, and that in a homophilic regime, it forms these nice stacks. And we'll now go on and look at how we could exfoliate graphene with it. Now, this is a topic, of course, that is hot, and there's many reasons why one should study graphene. And I'm not going to preach to the people here who probably know more about this area than I do. But from the point of view of using DAPP, then the idea was if they could be brought in to graphite and effectively challenge the stacking that we have in the graphite, they might be able to form this hybrid material and prise the graphene sheets apart. So the first indication that we could do this with the PF6 salt was just comparing, taking graphite in dimethylformamide and shining UV light on the sample. And the, of course, situation is that after about an hour of sonification, one sees here quite an impressive amount of fluorescence. And then when the graphene is present, that fluorescence, of course, is quenched because of the interacting with the pi systems. And this can be repeated in water using the chloride salt, exactly the same situation. You sonicate for an hour, and you have the control there between the ambient light and the UV light. You see the fluorescence, and it doesn't quite quench. It's obviously not as efficient, but there's still some considerable quenching as you carry out this process of adding the graphene with the DAPP. Spectroscopic analysis by fluorimetry also indicates that we're getting quenching as a result of adding the DAPP to the graphene. And the people in the graphene field, of course, characterize the graphene as a result of looking for the G band, which is expressing the planar configuration of the sp2 bonded carbons that actually constitute the material, and then the 2D band up here that is the way to get an idea of the thickness of the graphene layers. And what you'll notice here is that going from up here, where we don't have any DAPP, the intensity of the 2D to the G bands does increase, while the DAPP Raman frequencies are quenched. And this is indication that we are getting some insertion of the DAPP in between the graphene sheets. And you can look at this, of course, using scanning electron micrograph. So we have graphite, and then you can see these flakes that are effectively produced when you have the DAPP present. And then if you go to TEM, we can compare up here the chloride with the hexafluorophosphate. And again, you can see these flakes have been produced, revealing that there's some exfoliation of the graphene happening. And then finally, by AFN, we got a more quantitative measure of what was going on here, to the extent that the scans that went across these flakes indicated a distribution of heights that would suggest that we don't have a hugely efficient process. We have one or two in the region of what would be the graphene and the DAPP layers alternating like this, but I think we have a situation where we must concede that we probably have situations where we have graphene with several layers before the DAPPs intervene. So the system isn't super efficient. It's still under investigation. We've published the work, and we have a patent on it. And I think there's certainly interest in developing it beyond what I've told you in a commercial arena. And one of the reasons, of course, that I spoke about this work was I did want to make a connection here with the country I'm in. And HP, as we all knew him, he is now a CNRS researcher in Paris, and he spent a couple of years in Northwestern, and I think Jean-Pierre will remember because he was a constant visitor during this time, interacting with HP. And it was a pleasure having him with us. Okay, so now with that background, let's look at this area of supramolecular encryption. And here I'm back with ritaxanes again, but slightly different approaches. We have cucurbituril. Now we're down to CB6. We're going to have a couple of cyclodextrins, and they're both equally efficient. Beta and gamma cyclodextrin on the scene. And then these are the simple building blocks that we use because, you know, if you're going to go towards commercialization, things have really got to be very, very simple, and they've got to be efficient. And so Chen Feng devised this route to a ritaxane that the formation of it takes place in a minute at room temperature in water, and it's quantitative. And the situation here is that you build a 6 atom unit between these two ammonium sites, and this is just perfect to get this wonderful fit within the cucurbituril cavity of this triazole unit. And here you don't need any copper, of course, that would not be needed at all to carry out this reaction efficiently. Of course, it's not a catalyst, it's more or less a templated type of reaction. But why is it efficient? Well, the reason is that we have hydrogen bonding between the carbonyl groups here on the cucurbituril and on the cyclodextrins that are acting orthogonally. So we're getting molecular recognition not only at these points involving the cyclodextrin and the biphenyl unit, the cucurbiturils and the forming of their rings here, we're also getting it in the horizontal direction, and this accounts for the very high yield. So we came back then to DAPP and asked ourselves, because it's much larger, what would happen if we carried out the same reaction? And immediately you can see, okay, we have to heat now, it takes a little bit longer, and the yield is not quite so high, but I think that fits in with what we know about molecular recognition, because we've destroyed some of this hydrogen bonding. That cyclodextrin can't look at the CB on the right and the CB on the left simultaneously. But so what? This is what we managed to make, and the reason that we got excited about this was that if we looked at it in a situation where it was either dilute or the ends here, because these are pyrines, were capped with gamma cyclodextrin, then we saw still some fluorescence of the DAPP. We got a green fluorescence here. On the other hand, if we had a pretty concentrated solution, it gave rise to a red fluorescence. And our postulate is that the pyrene units here come and stack with this sort of vacant part of the DAPP unit. And we have more evidence, and much more than I'm going to show you the slides, involving CDs and all the rest of it, because we have a chiral unit here. But I don't want to use a lot of time going through a lot of detail. I just want to get over the principles. If we bring in a competitive binding agent, this adamantyl ammonium derivative, or its ammonium methyl analog, then we go back to a situation where we see red fluorescence, because this removes the capping units from the pyrene, the cyclodextrins, and produces a red color. So how could this be used in a way that would be perhaps commercially useful? So the point is that what I've shown you is just a very simple mixture of very quickly obtainable materials or cheaply obtainable just directly from the manufacturers. And here what you see is some ink pens that Chen Feng put together containing the constituents that you see here. So the competitive binding agent, the cyclodextrin, the fully capped situation, and the one without the caps. And before we look at a movie that's coming up here, just point out that when we start out without the capping, we have this exoplex probably being formed between the pyrene and the DAPP. And so we see this orange color. And then as we cap the pyrene unit with increased amounts of cyclodextrin, we see the green fluorescence that comes from the sort of native unit here that is not capped, this one here. And this is, of course, reversible in a very quick and supramolecular way, because if we add the competitive binding agent, this one here, then we go immediately back to an orange color. So the movie here is going to start with us writing with this capped unit, this one here. So this is pen 2, and you see NU, Northwestern University. And what's happening now, it's being written with the capping agent here, and this is giving us a kind of darker orange color for the adenine. And then what you're going to see next is the use of the pen that just has the cyclodextrin. And when the light, UV light is shown on, you'll see how the AD can be effectively erased in front of your very eyes. It's very, very quick, because it's a supramolecular situation where the bits and pieces are in equilibrium. And so why should this be important? Well, it's important because you have QR codes, you have barcodes that we're all well familiar with. And what we did was to take just a simple inkjet printer and replace the CMYK with the constituents that you see here, the ones that I've been talking about. And we're able to generate half rainbow, as we call it. It's minus blue at the moment. And the blue could be added on simply by adding in this pyrene derivative that you see down here. So this gives us a way of taking something with a digital input. We take this artwork here, and effectively, if we paint it not with the inkjet printer here, but with the one containing the supramolecular materials, then under natural light you can't see anything. But as soon as you shine UV light on it, it comes into, of course, glorious Technicolor. And so the point about all of this is that we have a nonlinear relationship between the ritaxane that we have put together very efficiently, the binding constants that we can play around with just simply by adding and taking away gamma cyclodextrin and or the competitive binding agent. And this is such that we can very finely change the color spectrum of the fluorescent images that we see depending on the content of the mixture that is used. And so you can see that just simply by going from one competitive binding agent to another, which has a stronger binding, we can get an increase in the green color here. If we decrease the amount of this competitive binding agent, we can increase the amount of the orange color. If we add the cyclodextrin here, but decrease its initial concentration from where it was, then we get less green. And then finally, if we add this one that introduces blue, we can introduce that into the spectrum. And then finally, from the point of view of having something that you could take to the marketplace, and what we're looking at here is, of course, counterfeiting. We can come in ultimately after we've got colors on a surface of some sort and carry out some authentication, because if we add almost anything that you care to think about, we can change the color in a way that is very, very unique to what we happen to add. And so the whole thinking here is if we were using just CMYK as a way of having some code on an article, then we have a fairly much linear relationship, and counterfeiters could easily decode this situation, and so reverse engineering is possible. On the other hand, we feel that what we have come up with here is a much more complicated yet simple system that allows security printing to take place, and it's a non-linear relationship, and so it gives us the opportunity to hopefully beat the counterfeiters. And on top of all of that, we have authentication tests to add on to it. Okay, so this was published fairly recently. It got a lot of press, and it is on the way to being commercialized. And the people behind this are this graduate student, Xixin Hu, who came to me from Hope College and is absolutely brilliant. And she's worked alongside Chen Feng. And the company involved here, I'll come back to at the end, is called Cyclodex, and it's headed up by Dr. Roger Petman. And this is Chen Feng. He has had an interesting career, starting off in China, spending a year in Japan while he was doing his PhD, had a couple of years as a postdoc in the UK, has had 4 years with me in Northwestern, and he's on his way to Dartmouth College to be an assistant professor in September. So at this point, I thought I would, since I've not gone very deeply into what I'm probably known for, just touch on some other areas. So I've talked about the supramolecular encryption, and you know, in the context of what are the big questions that are in front of us, I think we should be asking ourselves, as I say here at the bottom, can a conduit be established between fundamental science and economically viable applications? And we saw this yesterday morning from Jean-Marie with you know, the polymers that were self-healing and so forth. Another area that we are still very interested in is the mounting of switches into now robust environments. And these robust environments are metal organic frameworks. And I'm very privileged in being able to collaborate. And the great thing about Northwestern is, as we say, we hunt in packs. And so in this case, we're hunting with my colleagues Joe Hupp and Omar Farah to carry out self-assembly, solvent-assisted ligand incorporation here into a zirconium-type metal organic framework of switches that are based on some of our radical chemistry that, you know, I'm not going to have time to talk about. And we're interested in these switches because we started this whole story way back when I went to UCLA. We had already in our pockets bistable catenanes that could be addressed electrochemically, and they found their way into devices in a collaboration with Jim Heath. And this particular one was our first publication describing a microswitch tunnel junction, a single one. In the course of time, we switched from catenanes to bistable rotaxanes, and by 2007, we got to the point where we had a 160 kilobit random access molecular electronic memory patterned at this level, which is a very, very small level. It's less than the cross-section of a white blood cell. We, at the same time, did a lot of physical organic chemistry to establish that in the switching area, the way that the molecules switched the various ground states between what we call the ground state and the metastable state of the switch, the off state and the on state of the switch, they were not altered significantly as we went from one environment to another. What did alter was the size of the energy barrier from getting back from the metastable state here to the ground state. And in solution, it was something like 16 kilocalories per mole, so it lasted for about a second. by the time we got to a sandwich and a molecular switch tunnel junction, it was taking an hour and associated with a barrier of 22, 23 kilocalories per mole. But the downside of this situation is that switches would die after about 100 cycles. And so we've been looking ever since to get a situation where we could introduce more robustness. And in the beginning, in collaboration with Omar Yagi, we started introducing switches into metal organic frameworks, but got frustrated by the fact that these donor acceptor ones effectively would not move in the framework because they wanted to sort of team up in a donor acceptor way with each other. And so what I was showing you was another approach, if I just go back, and that is a post-modification one where we introduce the switches into an area that is really quite vast and gives us the opportunity, hopefully, to get movement between stations eventually. And then other areas that we're interested in at the moment are also working away from equilibrium, and we heard a good bit about this yesterday, not only from Jean-Marie, but also from Ben Feringa. One of the big challenges I think we have, and we've all been doused through our undergraduate trainings and subsequently maybe our graduate trainings in doing chemistry at equilibrium. Well, there's no fault in doing that, and nothing wrong with it, but we know that if we're going to get movement involving molecules, just as we get movement involving anything relating to ourselves, then we need to be thinking about moving away from equilibrium. And so we've just published very recently what we call an artificial molecular pump, and this is based on radical chemistry that has been a very big development in my lab in the last 5 years, and it was amazing it took us so long. It took us the best part of 25 years from the time we brought the cyclophane that became known as a little blue box on the scene to realize that if we could reduce it and then present it with a thiologen that had also been reduced to both of them in terms of the bipyridinium units, radical cations, then my goodness, you get a very strong complex. And that's very interesting. And it's counterintuitive, really, but maybe not to theoreticians. The free radicals there love each other more than the free positive charges. So it comes together. And then, of course, as soon as you oxidize, you're back with 6 positive charges, and Coulomb helps you to get movement. And so we've been able to use this fundamental breakthrough to construct effectively a pump where we bring a very highly charged species here over a charged entity at the end here onto a recognition site simply by reducing it. And so under reductive conditions, we form this complex, and then when we oxidize for various reasons, it doesn't want to depart over the positively charged end here. We have what we call a speed bump or a green door here to allow it entrance into a long polymer. And at this stage, we've pumped a couple of rings onto this chain, and we're obviously looking to pump more rings on. Now, why should we want to do that? Well, the whole business of polyrotaxanes that are built up of rings that are in a unhappy situation in relation to their dumbbell component. You can call them enthalpy demanding or entropically distressed, if you like, situations, is such that they are going to give us networks in the context over here of a different approach to it that will allow us, in effect, to dissipate energy into materials properties. And there's well documented evidence from work by Ito in Japan that such polymers are going to be probably quite useful in terms of their ability to stand up to stress and strain and scratches and so on and so forth. So that's just a glimpse at some of the ongoing things. I come back to my roadmap, and I have a couple of slides now that take us into the anti-cancer realm, and here this is just completing the loop and bringing us back to where I started off. What we did was to not only work with DAPP with methyl groups at the end, but we had another 7, I guess, derivatives here. And all of these, apart from this very highly substituted one with these 2 isopropyl groups, crystallize. One we don't have a crystal structure of, I think, but where is it? 4. All the rest crystallize either as an ABC, as you've seen already for the methyl situation, or as AB. And these AB ones are just repeating AB units in a constant channel or a constant long array. However, here it does not stack, and the reason is very obvious because of the situation involving these bulky groups. And so we took, I think, about 10 different cell lines, and these are just in vitro studies. And the take-home message here is that for selected cells, and this was 6 of them, the fact that the DAPP in this particular derivative does not stack obviously aids and abets the ability to cut down on the percentage viability of these cancer cells, and you can see that the group here are all beating doxorubicin. We don't do so well down there. So that at least is encouraging. So the summary there is that modifying the nature and size of the 2 9 substituents allows the potency towards specific cell lines to be tuned, and the introduction of these very sterically demanding groups not only aids the solubility in aqueous solution, but increases the potency against the cell lines that we have tested. And that tendency to aggregate is at the bottom of the reason why this happens. The fact that this one can't aggregate means that it can play its role as at least anti-cancer type drug in terms of at least in vitro studies. The person who's led the charge here is this Australian postdoc, Carol Hartlieb, who's been with me for some time. Okay, so I have a few minutes left, and the story that I've told you here has been basically one that I wanted to relate to Jean-Marie. A little bit of Freudian slip there, yes? And I have a few people up here just to recognize that we do work as a team. But I want to pick out Carsten Bruns here because he's somebody you're going to hear more about. Carsten was someone who, I told you about this hunting in packs, so he was somebody who initiated that right from the very beginning. He said, I'm going to, I hope, work with you, Fraser, and with Sam Stoop at the same time. And I know that Sam was here last week, and we worked together on many different things. And Carsten bridged this gap so beautifully that effectively he left Northwestern last year with a couple of PhDs. And the other remarkable thing about Carsten is that he writes much better than me. He illustrates much better than me. And so we've teamed up before he left Northwestern in March of last year to go to Berkeley as a Miller Research Fellow to start the writing of a book on the mechanical bond. And I've got good news for you. We're, I think, 85% of the way there. September will see the end of a long and arduous period of blood, sweat, toil, and tears, if I can quote Churchill. And I think here in Europe, with the help of Peter Gurlitz and Eva Witte, I hope we can sort of open the door. What really gets my goat is you can publish in Angewandte Chemie literally in hours. It's going to take, I'm told, 7, 8, 9 months to publish a book with Wiley. There's something wrong here. Yeah? Can we start a revolution in terms of getting the journals to tell the book people how to move things along? Okay. All right, enough of that. Okay, now the story of real serendipity. And one of my heroes, Ernest Elliot, when he was president of the American Chemical Society back in '92, had a little, I guess, magazine almost, that drew the analogy between what happens in science in one way and what happens in another. And so he took what was Ceylon, it's now Sri Lanka, but before even these names, it had the name Serendip associated with it. And probably this is just folklore, but there was a king who had 3 sons, and he said to them, go out into the world at large and try to do something about the dragons that threaten the island, but at the same time, keep your eyes open and see if there's anything else that comes to view that, you know, could be useful. So the 3 sons went out, and look what they did. They solved mysteries. They saved the nation from starvation, etc., etc. Rescued a lost princess. Came back, were showered with jewels and rare books, and look, hoards of gold again, yeah? And then the king said, well, maybe one of them or all of them are fit to succeed me. And so when we look at research, I guess there's 2 extremes. There's the Edisonian approach, where you know, it's all highly orchestrated beforehand, and it seems to be that that's where most of the funding agencies across the world want to be, under political instruction, and probably our involvement quite willingly with that, unfortunately. And then there's the other approach where, as the story tells, things just happen that were unexpected. And so he gives the example of Teflon. I would bring, of course, to the fore the example of fellow Scot Alexander Fleming, who gave us penicillin, to the point where, you know, just look at the person to your right or your left, and they wouldn't be there if you were here 100 years ago. It was transformative. Okay, so my first story of serendipity is we are trying to make Borromean rings. So something very, very esoteric and fundamental, and Jean-Pierre knows what I'm talking about, quite challenging. We had managed to do this with 3 rings that are of the same constitution, but it would be nice to see if it could be done with 3 rings of different constitutions. So one of my postdocs is taking gamma-cyclodextrin and azobenzene dicarboxylate as potassium salt, and this should form a 2-to-1 complex, and this would give us a cyclodextrin ring and the makings of a second ring, in case, including the 2 azobenzene units. Okay, so what happened was that we had this spoonful of sugar, the gamma-cyclodextrin, and we had salt in the form of the potassium salt, and this was done in aqueous methanol, but it could be equally aqueous ethanol, and we get crystals. And so we're excited, and we think that we're ready to go to the next step, when the crystallographer points out, oh, no, you've not got what you want. I don't see any azobenzene dicarboxylate at all. All I see is the cyclodextrin, which is basically the red here, and the potassium, which is the purple. And you have an extended structure. And it's become known as CDMOF, cyclodextrin metal organic framework. And it's built up of cubes, body-centered cubes, where you have gamma-cyclodextrin linked through their primary hydroxyl groups with potassium ions to fill up, or to join these 6 cyclodextrins together. And then they are linked through the secondary hydroxyl groups on the sugar to their neighbors, so that you get this extended structure, again, by potassium ions. Here's another sort of colorful representation. And here's a slice through that shows you that we have a cavity in the middle. It's around 2 nanometers in diameter. Cavities that you see here that are circular are the cyclodextrins. They're just under 1 nanometer, and they form channels in orthogonal directions throughout the crystal, as do these triangular cavities that are between the cyclodextrins. And all of this can be visited to do a lot of very interesting research, even that depends on the whole situation being chiral. So CD-MOF, as we call it, 1 is the potassium salt. CD-MOF2 we can make with rubidium, and CD-MOF3 with cesium. You can also make 1 with sodium. And they're very easy to obtain. This is the point, that basically it's what I call Bob's your uncle chemistry. You mix A, B, and C, or A, B, and C, and within hours you have these large cubic-sized crystals. It's even so easy that one of my ex-graduate students, Brian Northrop at Wesleyan College, has come out this year early on with an article in the Journal of Chemical Education based on what they're able to do in the undergraduate lab there, and what's more, he's published it with a high school teacher. So this is also being carried out in a high school. So what we have here, and this plays back to the last lecture last night. I wish I had been up on the stage as well, because here I have a food-grade solution to making food. You take gamma-cyclodextrin, which is a very good food-grade material, passed all the tests, some potassium benzoate, a food preservative, water, I hope that's all right, and high-proof ethanol. Well, that's okay in France as well. And you mix all this together, and you have something that is safe, cheap, and easily made. And it's a porous material. And why should that be useful? Well, industries that are based on food, we'll take first of all, personal care and home care are sitting ducks for this particular easy to get your hands on self-assembled material. And that's the basis for a first startup company called Panacea Nano. This man here is just, after 15 years, given up his job at Intel to establish this company with his eye very much on what you see here. Okay, so I'm going around the world preaching, without giving much thought to it, that it doesn't matter a damn what the anion is. It could be fluoride, it could be chloride, bromide, iodide, acetate, trifluoroacetate, you name it. It doesn't matter. That we'll get CD-MOF, 1. And then along comes a Chinese postdoc, Jishan Liu, and Jishan writes English marvelously well, but he's very difficult to communicate verbally, and I still don't know why he took to tetrabromoorate as the anion one day, but he comes to me and says, I don't get these cubic crystals, Fraser. They're big, long needles. And what's more, they appear in 5 minutes from aqueous solution if I go from gamma to alpha cyclodextrin. And so we look at them, of course, under all kinds of spectacles that you can use. But this really raises a red flag, and it certainly does not form a CD-MOF. What it does, it forms more classical long channels, and so you see under the scanning electron microscope here very, very long needles, just as we saw before with the DAPP. At this time, what we're looking at are long supramolecular, what I'd call pseudorotaxanes, where the diameter of these ranges between 100 and 500 nanometers. And if you take the 100 nanometer needles, they have roughly 4,000 one-dimensional supramolecular nanoassemblies right down that direction there. And the interesting thing is that it is very selective. This is coming up to, this whole business of molecular recognition and the lock and the key that we heard about at this time yesterday. It's only alpha cyclodextrin that precipitates like that in a minute. We can, of course, be a little bit more patient and wait and get crystals of the others in the course of time. And that's what happened. Jishan, very, very fine chemist, grew crystals from alpha, beta, and gamma with the bromide, tetrabromide, also with the tetrachloroaurate. And these are just two different views. And you can immediately see from these crystal structures why the alpha bromo clunks out of solution. Here we have a very solid interior here. Here we've got big spaces, spaces that even get so large and devoid of any counter ions. They must be swimming around somewhere. They're not being catched in the X-ray anyway. And the contrast is such that you can see why this one comes out from solution so readily. And if you do some BET surface measurements, of course, it tells you that, well, there's not much space in here to park anything, whereas there begins to be a lot of space in these ones. And then when those ones have not even got the potassium ions to hold together, they just collapse during the experiment here. And it's hugely selective. It's gold, and it's gold alone. You try platinum or palladium, and you're not in the business. And so if we just dissect the crystal structure, which it doesn't want to do, apparently. Okay, well, I missed a slide. So what? Probably against the clock. This shows very well what I want to talk about. It's a 2-to-1 complex. We have two rings around what turns out to be a potassium with 6 waters, so it's octa-coordinated. And here's our tetrabromoaurate. And notice how here the methylenes of the primary hydroxyl groups are pointing into the bromines here, so CHBr interactions. Now we're looking at the water where it'll be involved in OHO interactions with the cyclodextrin. And then you have interactions across here that are hydrogen bonded. And of course, all of this is probably dictated by some hydrophobicity. And don't forget the electrostatic charge, the plus and the minus that are being matched up here. So you bring together everything, and this is really a hand-in-the-glove fit. We don't get anything that really matches it. It's absolutely specific for the potassium tetrabromoaurate. You can look at it under the AFM and see them in real life here. The donut-shaped objects of the cyclodextrin and the distances match very nicely. And when we went to publish it, a reviewer came back and said, well, it would be more convincing if we actually took some gold that was an alloy and purified it. And so we went through this routine. We took aqua regia, which of course is a pretty devastating reagent to start with, got to the acid here of the bromoaurate. We neutralized it, got our potassium salt, added the cyclodextrin, filtered off the gold after we had carried out a reduction here, and we could, in principle, recycle the cyclodextrin. And so what Jishan was able to do was to go from a 58% or 14-karat gold in one fell swoop in 91% yield to 24 almost karat gold. And this is the flow chart for the whole scene. Since time is not on my side, I will just say gold is big the world over, of course. China in the lead, Australia, United States. There's a lot, even in my own native Scotland, there's gold, believe it or not. Now, the bad news is that it's extracted today, 83% of it with cyanide, and almost the rest of it with mercury. So 2 very obnoxious chemicals. And the situation is such that there have been spills all over the world, and it's very interesting. The big mines are still, headlong into cyanide, and it's never going to change, and so on and so forth. But I think as time goes on, our process of bromination, which is fast compared to cyanidation, It's green compared to cyanidation. It's flexible, and we can beat it out in terms of profitability. But above all, it's green and it's environmentally friendly. And I just want to finish with almost this last slide. The biggest experiment in supramolecular chemistry is about to take place in Nevada. And what happens there is that they gouge out of the ground near some gold ore reserves a space the size of a football pitch. And they line it with plastic, and they bring in the ore, and then they have a system of sprays that go back and forth, spraying cyanide down on top, and then it goes on from there. So we're apparently going to get a third of a football pitch to carry out this experiment. And this startup is Cyclodex, and I'm overjoyed that it's been led by my fourth graduate student, whom, where's Jonathan? Here, knows very well, Roger Petman. Quite a guy, isn't he? He's done extremely well. He had 20 years in a more traditional setting of Shell and I think Bayer. But now, for many years, he's been freelance and been very, very successful, picked up honorary degrees, and well, it's in his hands, and we wait to see if he can bring that particular very serendipitous invention that is very, very simple, based on the science that we all do. Now, we're with gold, so it's a golden jubilee, Jean-Marie. You started off there, went there, been there. We saw about that yesterday, and that, and that, and that. So the question is, what's next? Okay? The next one is coming along in 2025. But before then, I'd like to give you a present. And it's 16 catenane. I hope it's 24 carat, and it's made of gold.
Thank you very much.
Yeah, we should have a photograph.
Maybe I should go.
You should show the gold.
Show the gold.
Yeah.
Sure. Here it is.
Yes. Good.
Thank you very much. Is that your process?
Oh, not yet.
Not
But,
yet.
but it
When
will
you
be
have your
soon.
process, it gets even longer.
It'll get even longer, yeah. And the challenge to make the polycatenane will be even bigger.
Good.
Good.
Thank you very much.
Thank you.
Thank you, Fraser, for this beautiful and very inspiring talk and mixing of fundamental and applied science. I really enjoyed that. So I think we can have some questions.
Really?
No?
Okay. We're not allowed to, I don't think.
Then, well, I like questions. Okay. But before we go to coffee at the moment, because I have a small gift for Fraser to remember this day and this event. So you have one of these dishes for the lab.
Thank
Len.
you. Thank you. It's gold. Yeah, it's gold, it's gold.
Oh, it's the encryptic fluorescence ink. Thank
you
so
very much. Thank you.
Thank
Thank you.
Okay, so I invite everybody to have coffee.